Welcome everybody. That's the second session of the morning. So, and since we are really short in time, so I don't go with introducing people and speakers. So, and most of the people, you know each other. We are a family, as mentioned in the previous talk. So, the first speaker in the morning is Professor Nader Engheta from University of Pennsylvania. So, let's welcome him.
Thank you very much, Ibrahim. Today is a great day for all of us because we are all celebrating our dear friend, Bob Boyd's birthday. Bob, happy birthday to you. We have known each other for many years, and you're an amazingly intellectually curious person. A lot of inspiration you have given to all of us, in the community. I'd like to thank you so much for being you and really encouraging and inspiring all of us. And I look forward to many, many more years of interaction and collaboration together. I want to thank also the organizer, Ksenia and Ibrahim and their teams for putting together this wonderful celebration and bringing all of us together. When Ksenia and Ibrahim asked me to participate and give a talk, I said I'd be more than happy to do that. Bob is my great friend. And so I was thinking what topic I'd like to talk about in this great celebration, Bob. Now, Bob knows that I like very much the topic of ENZ, light-matter interaction. And we've been working that for several years. And he likes it very much too. And in fact, recently we started a collaboration together. But I decided not to talk about ENZ for two reasons. One is because Bob is going to talk about that later on in the meeting, so it would be great to hear it from him. And the second reason is I know he's very curious intellectually. So I decided to talk about a topic that he hasn't heard from me before, hoping that that would actually trigger another avenue for the collaboration between our two groups. So what I'd like to talk about today is what is it that recently we started looking into that, which I call it four-dimensional metamaterials. Now, we all know, by the way, in Maxwellian electrodynamics, space and time are very much interrelated. So many features that we have in space, of course, we can reflect that in time. Now, in the area of metamaterials, most of the work in the area of metamaterials is actually dealing with spatial inhomogeneity. So we make metasurfaces with spatial inhomogeneous structure, volumetric, and so on. So we decided to actually look at the dual of that. In other words, could we have materials that the parameters of that will change temporally, and to see what interesting similarity and differences we get. Now, we had two sources of inspiration for this. One is the concept of time crystal. In 2012, Nobel laureate Frank Wilczek introduced the concept of time crystal. So what he was saying is that we know, by the way, in crystal is a periodic distribution in space of atomic structures. So what he proposes, what would happen if we have a periodic distribution in time? Could we have a matter that would be called time crystals? Now that created a lot of interesting debate and discussion. And then last year, two experimental groups, Michelle Looking from Harvard and Chris Monroe from University of Maryland, experimentally shown that indeed they can have time crystals. So that was one source of inspiration for us. And another source is the work of my great friend, Matthias Fink from Institut Langevin, who has done a lot of fascinating work in time reversal systems to show how actually some of this interesting time reversal system can lead to interesting phase conjugation. In addition to that, the fact that we've been working on metamaterial, particularly in the spatial domain, we wanted to see what happens just out of curiosity if we actually bring that concept in time. So when we started looking at literature and see what has been done, we find that actually this is a very, very rich topic. The time-dependent platforms, by the way, has a very long history in electromagnetics. In fact, the earliest paper I was able to find belonged to Morgenthaler in 1958, in which he showed what would happen if you have a medium in which electromagnetic is propagating and then rapidly you change the phase velocity of the medium there. What would happen? And over the years, there are a lot of groups actually working on time-dependent platforms. So we said, let's find an interesting topic that nobody has done before in this concept. And I'm going to tell you what it is that we are doing. But before that, in the next 6 slides, I will show you a background for this issue of temporal platforms. Now, if you look at the issue of temporal, as I mentioned, space and time are very directly connected to each other. So in space, by the way, the simplest possible problem that we tell our student is basically Fresnel reflection and refraction. So this is just undergraduate. The first topic we tell our student that if we have a medium that has 2 segments, one epsilon naught, the other one epsilon 1, which means in space is a function of 1 variable, then what happens? And of course, we know what happens. Wave comes over here, we have a reflection and transmission. What is the analog of that in time? In other words, imagine that you have a medium that is unbounded in space, has a certain permittivity, and then at the time t equal to t naught, you rapidly change the permittivity of the entire medium while the electromagnetic wave is already there. What happens to that wave? Now, this problem, by the way, has studied before, and in fact, there are 2 interesting so-called the temporal boundary condition you have to take into account. One is that if we actually go back to the space boundary before, we know, of course, Maxwell's equation has to be satisfied everywhere, including going through the boundary. And because in space, we have a variation in space, we have to make sure that the derivative with respect to space stay finite. So as a result, we have to make sure that the curl of E and curl of H stay finite. And of course, that leads to the very well-known boundary condition we learned in the first course in undergraduate electromagnetics. Tangential E continuous, tangential H continuous, normal B, and normal D. And those are all related to the space derivative in Maxwell's equation. By analogy, if I have something in which you have a medium that is unbounded, and then at t equal to t naught, you rapidly change permittivity of that, or permeability, or both, then we have to make sure that the temporal derivative in Maxwell's equation stay finite. As a result, the temporal boundary requires that vector D to stay the same just before t naught and just after t naught, and vector B stay the same just before t naught and just after t naught. A consequence of that is that electric field can actually have a jump, and the magnetic field H can have a jump. So that's one interesting boundary condition that we have to take into account. But another interesting condition is relation between frequency and wavelength in temporal metamaterial. Now, what that means is that, again, if I take you back to the very well-known case of Fresnel reflection and refraction, we know that if you have 2 media in space and we send a wave with a momentum k1 and frequency omega 1, when this wave enters into other medium, obviously it has the same frequency for the linear medium. But the wave numbers would be different, and the wavelength would be different because phase velocity changes. However, if you do that in the temporal domain, what remains the same is the wavelength, but the frequency actually will have a jump. In other words, if we have a medium which is unbounded and electromagnetic monochromatic wave is already there, and then at t equal to t naught, you rapidly change the permittivity, the wavelength of that wave stays the same, but the frequency of that will change. And as a result, we have to make sure that this condition should always satisfy in that rapid variation. Now, this actually could lead to interesting possibilities, because that means that suddenly the photon energy will change. So the question is, where does that energy come from? That energy comes from the action you actually perform on the medium. This is very different than the spatial change that we have in the space, in the Fresnel one. In this case, you actually put the energy into the system, and photon energy will change. This is known as photon acceleration, by the way, in the plasma physics community. In plasma physics community, people have looked at this scenario. What would happen if inside the cavity, you suddenly change permittivity of a medium, and the frequency rapidly changes inside the cavity. Now, so if I have a monochromatic wave propagating inside the medium, and at t equal to t naught, rapidly you change permittivity, we just learned that the frequency of that will change, but the wavelength stay the same. But at the same time, that wave actually split into 2 waves. One keep going forward, the other one would be backward. In other words, if you start with a monochromatic wave like this, and then suddenly you change permittivity, you notice wave number K1 stayed the same in this, but then omega 1 is not omega 1 anymore. It becomes omega 2. The question is, what is the relation between the magnitude of these two waves, forward and backward? Now, Govind Agarwal in 2014 solved this problem. So what he and his group find out that you can have the so-called the reflection for the backward wave and transmission for the forward wave can be related to this very interesting set of relation. And by the way, this relation is very much analogous to what happens when we actually have a change of the permittivity in space. But this is change in time. Now you notice, by the way, that if I look at R and I square that, and I look at T and I square that, and I add them together, they're not going to be 1. That's interesting, and that's because you actually pump energy into the system. In fact, if we change the material from epsilon 1 to epsilon 2, and if the epsilon 2 is near 0, then R and T become very large, actually. Now that's quite interesting. So, let me show you just interesting in simulation just to give you a feel for it. This is a standard reflection and refraction that happens in standard boundary in space. But if you do that in the temporal boundary, something like that happened. So let me start again. And let me assume a bundle of wave is coming right now. You're going to see that. And then at t equal to t naught, you change it, split in 2, and actually goes faster. You notice that the wavelength doesn't change before and after. But the phase velocity does change, and as a result, frequency does change. Okay, now, so that's already known in the literature. So after we learned all of this, we said to ourselves, what could be an interesting things we can do that has not been done before? So we asked a simple curiosity-driven question, just purely a curious question. What happened if in a medium, I start with epsilon 1, which is positive, and I already have electromagnetic wave in it, and then at t equal to t naught, I change the permittivity from positive value to negative value. What would happen? Now it's interesting. Let's go back to this. We know that this condition should be satisfied. But here is an interesting possibility. If epsilon 2 becomes negative, remember these are all positive, of course, here. But if epsilon 2 becomes negative, that becomes purely imaginary. That means omega 2 should become purely imaginary. So in other words, what happens to that wave? So what happens is that this frequency becomes purely imaginary, which means the expression I showed you before that was one forward wave, one backward wave, they're not going to be wave anymore. Because this part is a function of time. They're not actually propagating. In other words, one of them exponentially grow, the other one exponentially decay in time. But the wave would be frozen over here. So we said, okay, this is just interesting result, but can we do such a thing? In other words, cannot we actually start with a medium that is epsilon is positive, and rapidly I change that to the value of epsilon negative? Now, then we run into this interesting, challenging question. We know from metamaterial and from a light-matter interaction that if I want to have a medium with epsilon negative, that epsilon has to be dispersive. In other words, it should be a function of frequency. Now, we started with a monochromatic wave, omega 1, but when we do this change, it becomes exponentially growing and exponentially decaying. That's not monochromatic wave anymore. So it has a lot of frequency in it. So in that case, how can I actually keep epsilon negative for all those frequencies? So we started with this paradox, and we said, let's see whether we can do such a thing. So first we started questioning what would happen if I want to do it with Drude model. So imagine, of course, in the Drude material that we are all familiar with, imagine I start with the material that has no electron density, so like free space. Epsilon 1 is this, and I have a frequency omega 1 propagated through here. Now, at t equal to t naught, I'm going to inject a lot of electrons into this medium, hoping that I increase omega p from 0, and hoping to make this thing negative, which of course we know that happens in Drude material. However, at the same time, I have to make sure this is always satisfied. So in other words, if I want to follow this one there, this omega cannot be my original omega 1 anymore. It has to satisfy this relation, so I have to put omega 2 there, and if I consider these two equations, I end up with these equations. And you notice that this omega 2 is always greater than omega 1. In other words, if you inject electron into this system, hoping that the system becomes negative, your omega 2 would increase such that it's always greater than omega p. As a result, this expression always stays positive. So I cannot do this with the Drude material. That's out of the questions. What should we do next? Can I use any other dispersion to do that? So we decided to look at this in a general way. But we all know, by the way, that if you use any passive medium, oh, I'm sorry. Is that okay? If we use any passive medium, we have to make sure that medium follows the Foster reactance theorem. Now, many of you are familiar with this, but let me just quickly review what's the Foster reactance theorem. If we have a one-port network, which is lossless or very low loss, we know that if we look into this network, I have an impedance, and that impedance is primarily purely imaginary, because almost lossless there. Now, it's known, by the way, according to Foster reactance theorem, that if I have an impedance like this, with a primarily imaginary part, and R is very small, that X as a function of frequency should always have a positive slope. That's part of the passivity of Foster reactance theorem. That's one of the reasons that usually when we look at the dispersion, we always have the positive slope here, positive slope here. Now, in this case, in the middle, we have negative slope, but that's, of course, anomalous refraction, and that, of course, we have a huge loss. But in the low loss region, always the derivative with respect to frequency should be positive. That's what in circuit, we have capacitor, and that's the impedance of a capacitor. You notice that it has a positive slope. If I have inductor, that impedance has a positive slope. If you put them next to each other, of course, you have a resonance. But you notice that the slope of the impedance is always positive with respect to frequency. The question is, if I want to have epsilon negative and hold it for all frequency as epsilon negative, then that means the slope of that with respect to frequency is not positive. So does it mean that I can find the material that would violate the Foster reactance theorem? The answer is actually people in circuit theory already have done that. In fact, in circuit, people back in 1950s and 60s developed circuits that's known as non-Foster circuit. In fact, if you look at, in non-Foster circuit in the circuit aspect is that the idea in circuit theory is that if you have a capacitor, regular capacitor that has impedance like this, can I have a capacitor that is negative C and stays at negative C for all frequency? If that's the case, then you notice the impedance has a negative slope. And can it be this thing built? Yes, they have built that. In fact, they have built it, but something known as negative impedance converter. Negative impedance converter in circuit, what it does is that you put a load, a regular load over here, but when you look into this load, this input impedance would be minus a constant multiplied by the load. In other words, if you start with a regular R plus JX, the negative impedance converter can make that minus R minus JX. In other words, it has to be a gain medium. A passive medium cannot do that. Negative impedance converter are actually a gain and active circuits. And in fact, this idea goes back to 1953. Linville in 1953 suggested a very interesting circuit by combination of two amplifiers and a regular load and two resistors. He actually created a system that's known as non-Foster circuit. In other words, yes, it is possible to create a negative capacitor that will stay negative for the range of the frequency. So with that encouragement, we said, well, let's come back again to material. So can we do this now? The answer is yes. So what happens is if we go over here, let me start with the vacuum first and with the frequency omega naught. And let me assume I would like to rapidly change that to epsilon minus 3. And in that case, omega 2 become purely imaginary. So what happens to the wave? So let's take a look at it. These are actually a plot in the analytical expression that I have. So imagine this is a function of a space, and you have an electric and magnetic field of a simple plane wave that's propagating. And this is at a given time. So you freeze the time. And at that time, rapidly you change epsilon from 1 to minus 3. As soon as you do that, you notice what happens to the electric field. Electric field rapidly switches from something, and you notice the magnitude of that become 1/3 because the vector D has to stay the same, and epsilon 2 is minus 3 with respect to 1. So electric field become 1/3 less. And actually, the polarity of that flips because epsilon 2 is negative. But the magnetic field doesn't change because we are not changing mu. As a result, this actually split. When it split, so remember the expression I showed you? This is the split of that. But this split is not really a wave. It's actually a frozen distribution over here. You notice wavelengths stay the same. But of course, wavelength become meaningless because this is not a wave anymore. It's just a frozen field there. And now let's see what happens if I let the time go by. So this is at the moment that this happens. If I do, 15% going in one period, you notice what happened. One of those frozen waves grows in time. The other one decays in time exponentially. If I wait, half a period, and I get to this, you notice one of them keep growing, the other one is decaying. If I wait one period, one of them is completely gone, the other one actually keeps growing. Now this is interesting. So in other words, you have already a wave that's what in the medium, and at t equal to t naught, you make the permittivity negative, which means you have to make the medium active. You pump it, wave freezes and grows there. But then, what do we do next? I don't want to have it grow because that grows forever. What if I bring it back again to the epsilon positive? So in other words, well, let me show you the simulation over here first. So you notice, let me just go over again. At the beginning, you have the wave. Let's just start all over again. It's coming. The wave is coming. Boom, you make it negative. This grows, this decays and freezes over there. Now, so what if we switch it back to epsilon positive after a very short period of time? You can bring it back to the original epsilon you had, or you can bring it back to another epsilon you want. In that case, what happens? I'm going to show you the result, but let me intuitively tell you what happens. You already have a wave propagating over here in a regular medium, epsilon 1. At time t equal to t naught, you make this epsilon negative, thing freezes, wave grows, and then a moment later, you bring it back. When you bring it back, that becomes a wave again. In this time, two waves on two directions. But this wave is stronger than the original wave you have. In other words, I call it like a filling stations. It's just like a car coming to a gas station. Wait, you pump the gas and goes. So this time, wave would come, you freeze it, you pump the energy into the wave, and then let it go. So let's see what happens. So here, this is the picture that we show over here. This is x and time, so you see this one wave that's going like this. At t equal to 4, you make the epsilon negative, the wave freezes, there's no variation with respect to x, but grows in time. And then at t equal to 6, you let it go. And then goes in both directions, in the positive x and negative x direction. So we want to implement this. So in order to implement this, we know in circuit we can have negative c. So I have a colleague next door who's expert in circuit theory. So we joined forces, we said, let's try to actually show this in circuit. So the idea that we are working, this is work in progress, by the way, literally as we speak. So we say if you have a transmission line which is a combination of L and C, that would be a regular medium. What if we actually bring and put this negative capacitance parallel with this, like this one, with the switches? So imagine I have all of these parallel, and then at t equal to t naught, I switch all those negative capacitors to this. The transmission line actually would freeze the wave there. It's automatically pumping energy into the system from that negative capacitor, and then at some other time we'll remove it, and this will go. So this is the analytical expression for this we have. You notice the wave is going. At this time, wave grows, and then we'll split it. And this is the numerical simulation for that. Now, my colleague and our two groups are working together. We have already designed the circuit. The circuit actually has been built. And right now, we're actually looking at troubleshooting it. We don't have the experimental result yet, but we are actually in that direction that we can. So we want to show that actually this is another way that we can actually amplify a wave in that regard. In the last 3 minutes that I have, let me just show you about one other topic and then I stand, which actually comes out of this curiosity-driven question we had. Now, as I mentioned in Maxwellian electrodynamics, there's a clearly connection between space and time. We all know that. But at the same time, there's a difference between space and time. In space, we have x, y, z. And we have x negative, x positive, z negative, z positive. But in time, because of causality, we always go one direction, and it's only one value. So we scratched our head and said, is it possible that we come up with an idea in metamaterial that actually give the time more than one dimension. So that's why they call it temporal anisotropy. So you say, well, in electromagnetics, I have a permittivity, but of course, so far, the permittivity I've shown was isotropic. But what if I assume the permittivity is anisotropic? In other words, when I want to change at time t equal to t naught to a different permittivity, I have it two different values depending on epsilon xx or epsilon yy. What interesting things we can get. So let's go back to this, what I showed. The permittivity is isotropic here, and t equal to t naught, the medium suddenly becomes a crystal. In that case, vector d should stay the same. That's a temporal boundary condition. But that means because epsilon 1 and epsilon 2 are two different tensors, the direction of electric field would flip. And when the direction of electric field flips, the Poynting vector would flip. So interesting phenomena happens. So you're suddenly going from an isotropic, sphere of index to anisotropic ellipsoid of index. And in every direction, the wave number should stay the same. That means in every direction, the frequency will be different. You're going to have a rainbow effect. So let me show you this result. So you have a dipole antenna that you have over here that's propagating regularly in those directions. And t equal to t naught, you change this to an anisotropic crystal. See what happens. Look at the direction of energy flow. In the direction of energy flow actually switches. Go the other direction. Let's do it one more time. You'll see. It comes, it's a regular dipole, and then suddenly it goes the other directions. So by doing that, you can actually manipulate the radiation pattern of a radiator without touching the radiator. It's just by rapid variation of the permittivity you can do that. And depending on whether which one is bigger than the other one, the pattern can go in different directions. Now, finally, I mentioned about the rainbow effect. This is an interesting analogy, by the way. In space, when I send the wave, and I have a scatterer over here, when the wave hits this one, it scatters in different directions. So in different directions, we have different wave number, but the frequency is the same. What if I want to do this in time? The wave is going like this, and suddenly I change this to an anisotropic medium. Wavelength stay the same, wave number stay the same, but in every direction, frequency becomes different. So that becomes truly a rainbow. So this frequency would be a function of angle of observation. In other words, you have a phenomenon, something like this. So let me show you this. This is the wave is coming through this aperture and radiates, and then suddenly you change that and you see what happens. The wave first comes from the aperture, coming like this, and then you rapidly make it anisotropic, and wave goes in different directions. So if you stand in different angles and measure the time history of the wave, you get this one. In 90 degrees, you get this time history. In 80 degrees, you get this time history. In 0 degrees, you get this time history. And clearly, you see the different frequency. In fact, if you do the FFT analysis, you see in every angle direction, you have a different frequency. So you start with monochromatic signal, single source. You make the medium, the entire medium, change the same way, and yet in every direction, you have a different frequency. So let me stop over here, and thanks organizer, and particularly my good friend, Bob Boyd. Happy birthday, Bob. Thank you.
I know that you have questions, only Bob can ask questions. Because we don't have time. Bob, you have a question. Sorry, guys.
Okay. Yes.
Best question answer tonight.
Bob, you will have a second chance.
You have a second chance. Zahir.
So the question is, of course, you said you're not going to talk about the energy, but you really talk about the energy.
One slide.
But all the effects that's really done in this domain, what you mentioned, you use non-linear medium in some sense. So the question is that in multi-linear omega p, so Drude model, there you say that omega in Drude material, you cannot do this.
No.
So what was the logic?
Well, the logic is this. So let's assume you, by the way, all of this thing I said, electromagnetic is already there. I'm not talking about the incoming with interface. It's already there. As you pump electrons over here, hoping to bring omega p up, the problem is the frequency also changes. And the frequency, when it changes, the frequency always becomes greater than omega p. So as you're increasing omega p, omega is always greater than omega p because of the other condition. So that epsilon always stays positive and approaching 0. So when it approaches 0, omega 2 becomes infinite, in principle.
Right.
So you can never make, in a passive medium, you can never make it.
In passive.
In passive, exactly. Drew the model in the passive medium.
Right. So when you pump, then you see.
Then in pump you can do it. Absolutely. Yes, in pump you can do it.
Okay, now. Okay, Paul.
I have a
Please.
really quick question, issue of detail. You said that the x, the omega has to be positive.
That's right.
Then you showed an x is a function of frequency and it was a Lorentzian.
Yeah.
So the slope is positive on one side with negative on the other side. So I missed.
Oh, miss, okay. The Foster reactance theorem says that the dxt omega should always stay positive when there is low loss or lossless. So you see that this is positive, but when you get that's one negative, that's the area of anomalous refraction, you have a lot of loss. So Foster reactance theorem would allow you.
Only outside.
Yeah, exactly. Always in the region of the low loss or lossless. Yes, that's the passivity of the medium.
Ora, very quick, please.
So you showed quickly permittivity before the last section, before the rainbow section. You showed the permittivity doing something like this.
Yeah.
When I see that, I think of like a cavity, right? You have low index, high index, low index.
In time.
That's the point, right?
Exactly.
So in space, when you have a cavity, you end up getting a frequency, a very narrow bandwidth. So in time, when you have a cavity, what you get in
Yeah.
what you get, yeah.
Excellent observation. Yes, that's exactly right. There's a lot of interesting analogy between the two. Yes, that will give you also a cavity, but because that is the active medium, the energy grows in that region. So in other words, it's like a temporal cavity. You're absolutely right. It's temporal cavity, but this temporal cavity, the value of the field is higher than when you started.
But is there an analogy where it's like trapped in a like
Yes.
in K vector, for instance?
Yes, we are studying that. Yes, and in fact, it's very interesting. You can actually have an analogy of the antenna within the photonic crystal. You can do that in time.
Okay, there's no further questions. Let's thank you.
Thank you.